For many learning algorithms, among them linear regression, logistic regression, and neural networks, the way we derived the algorithm was by coming up with a cost function or coming up with an optimization objective, and then using an algorithm like gradient descent to minimize that cost function. When you have a very large training set, gradient descent becomes a computationally very expensive procedure. In this video, we'll talk about a modification to the basic gradient descent algorithm called Stochastic Gradient Descent, which will allow us to scale these algorithms to much bigger training sets. Suppose you are training a linear regression model using gradient descent. As a quick recap, the hypothesis will look like this, and the cost function will look like this, which is this sort of 1/2 of the average squared error of your hypothesis on your M training examples. And the cost function, we've already seen, looks like this sort of bowl-shaped function. So plotted as a function of the parameters theta 0 and theta 1, the cost function j is a sort of a bowl-shaped function. And gradient descent looks like this, where in the inner loop of gradient descent, you repeatedly update the parameters theta using that expression. Now, in the rest of this video, I'm going to keep using linear regression as the running example, but the idea is here, the idea of stochastic gradient descent is fully general and also applies to other learning algorithms like logistic regression, neural networks, and other algorithms that are based on training gradient descent on a specific training set. So here's a picture of what gradient descent does. If the parameters are initialized at a point there, then as you run gradient descent, different iterations of gradient descent will take the parameters to the global minimum. So take a trajectory that looks like that and heads pretty directly to the global minimum. Now the problem with gradient descent is that if m is large, then computing this derivative term can be very expensive because this requires summing over all m examples. So if m is 300 million, right, so in the United States there are about 300 million people, and so the US or United States census data may have on the order of that many records. So if you want to fit the linear regression model to that, then you need to sum over 300 million records, and that is very expensive. To give the algorithm a name, this particular version of gradient descent is also called batch gradient descent. And the term batch refers to the fact that we're looking at all of the training examples at a time. We call it sort of a batch of all of the training examples. It really isn't maybe the best name, but this is what machine learning people call this particular version of gradient descent. And if you imagine really that you have 300 million census records stored away on disk, the way this algorithm works is you need to read into your computer memory all 300 million records in order to compute this derivative term. You need to stream all of these records through computer because you can't store all your records in computer memory. So you need to read through them and slowly, accumulate the sum in order to compute the derivative. And then having done all that work, that allows you to take one step of gradient descent. And now you need to do the whole thing again. Scan through all 300 million records, accumulate these sums, and having done all that work, you can take another little step using gradient descent, and then do that again, and then let's you take yet a third step, and so on. And so this can take a long time in order to get the algorithm to converge. In contrast to batch gradient descent, what we're going to do is come up with a different algorithm that doesn't need to look at all of the training examples in every single iteration, but that needs to look at only a single training example in one iteration. Before moving on to the new algorithm, here's just the batch gradient descent algorithm written on the game, with that being the cost function and that being the update. And of course, this term here that's used in the gradient descent rule, that is the partial derivative with respect to the parameters theta j of our optimization objective, j train of theta. Now let's look at the more efficient algorithm that scales better to large data sets. In order to work out the algorithm, it's called stochastic gradient descent, let's write out the cost function in a slightly different way. We're going to define the cost of a parameter theta with respect to a training example xi comma yi to be equal to 1/2 times the squared error that my hypothesis incurs on that example xi comma yi. So this cost function term really measures how well is my hypothesis doing on a single example xi comma yi. Now you notice that the overall cost function j train can now be written in this equivalent form. So JTrain is just the average over my M training examples of the cost of my hypothesis on that example xi, yi. Armed with this view of the cost function for linear regression, let me now write out what the stochastic gradient descent does. The first step of stochastic gradient descent is to randomly shuffle the data set. So by that I just mean randomly shuffle or randomly reorder your M training examples. It's sort of a standard pre-processing step. Come back to this in a minute. But the main work of stochastic gradient descent is then done in the following. We're going to repeat for I equals 1 through M. So I'm going to repeatedly scan through my training examples and perform the following update. I'm going to update the parameter theta j as theta j minus alpha times h of xi minus yi times xi j. And we're going to do this update as usual for all values of j. Now you notice that this term over here is exactly what we had inside the summation for Bash gradient descent. In fact, for those of you that are familiar with calculus, it's possible to show that that term here, this term here, is equal to the partial derivative with respect to my parameter theta j of the cost of the parameters theta on xi, yi, where cost is of course this thing that was defined previously. And just to wrap up the algorithm, let me close my curly braces over there. Okay. So what stochastic gradient descent is doing is actually scanning through the training examples, and first it's going to look at my first training example x1, y1, and then looking at only this first example, it's going to take like basically a little gradient descent step with respect to the cost of just this first training example. So in other words, it's going to look at the first example and modify the parameters a little bit to fit just the first training example a little bit better. Having done this, inside this inner for loop is then going to go on to the second training example. And what it's going to do there is take another little step in parameter space, so modify the parameters just a little bit to try to fit just the second training example a little bit better. Having done that, is then going to go on to my third training example and modify the parameters to try to fit just the third training example a little bit better, and so on until it gets through the entire training set. And then this outer repeat loop may cause it to take multiple passes over the entire training set. This view of stochastic gradient descent also motivates why we wanted to start by randomly shuffling the data set. This just ensures that when we scan through the training set here, that we end up visiting the training examples in some sort of randomly sorted order. Depending on whether your data already came randomly sorted or whether it came originally sorted in some strange order, in practice this could just speed up the convergence of stochastic gradient descent just a little bit. So in the interest of safety, it's usually better to randomly shuffle the dataset if you aren't sure if it came to you in randomly sorted order or not. But more importantly, another view of stochastic gradient descent is that it's a lot like Bash gradient descent. But rather than waiting to sum up these gradient terms over all M training examples, what we're doing is we're taking this gradient term using just one single training example, and we're starting to make progress in improving the parameters already. So rather than waiting till we've taken a pass through all 300,000 United States Census records, say, rather than needing to scan through all of the training examples before we can modify the parameters a little bit and make progress towards the global minimum. For stochastic gradient descent, instead, we just need to look at a single training example and we'll already start making progress in the space of parameters towards moving the parameters towards the global minimum. So here's the algorithm written out again, where the first step is to randomly shuffle the data, and the second step is where the real work is done, where that's the update with respect to a single training example xi, yi. So let's see what this algorithm does to the parameters. Previously, we saw that when we're using Bash gradient descent, that is the algorithm that looks at all the training examples at the time, Bash gradient descent would tend to take a reasonably straight line trajectory to get to the global minimum like that. In contrast, With stochastic gradient descent, every iteration is going to be much faster because we don't need to sum up over all the training examples, but every iteration is just trying to fit a single training example better. So if we were to start stochastic gradient descent, let's start stochastic gradient descent at a point like that. The first iteration, may take the parameters in that direction, and maybe the second iteration, looking at just the second example, maybe just by chance we get a little unlucky and actually head in a bad direction and move the parameters like that. In the third iteration, where we try to modify the parameters to fit just the third training examples better, maybe we'll end up heading in that direction. And then when we look at the fourth training example, maybe we'll do that, the fifth example, sixth example, seventh, and so on. And as you run stochastic gradient descent, what you find is that it will generally move the parameters in the direction of the global minimum, but not always. And so take a somewhat more random looking and circuitous path towards the global minimum. And in fact, as you run stochastic gradient descent, it doesn't actually converge in the same sense as batch gradient descent does. And what it ends up doing is wandering around continuously in some region close to the global minimum, but it doesn't actually just get to the global minimum and stay there. But in practice, this isn't a problem because, so long as the parameters end up in some region there, maybe it's pretty close to the global minimum, so long as the parameters end up pretty close to the global minimum, that will be a pretty good hypothesis. And so usually running stochastic gradient descent, we get a parameter near the global minimum, and that's good enough for almost essentially most practical purposes. Just one final detail. In stochastic gradient descent, we had this outer loop repeat, which says to do this inner loop multiple times. So how many times do we repeat this outer loop? Depending on the size of the training set, doing this loop just a single time may be enough, and up to maybe 10 times may be typical. So you may end up repeating this inner loop anywhere from once to 10 times. So if you have a truly massive data set like this US Census dataset example that I've been talking about with 300 million examples, it's possible that by the time you've taken just a single pass through your training set, so this is for I equals 1 through 300 million, it's possible that by the time you've taken a single pass through your dataset, you might already have a perfectly good hypothesis, in which case, this inner loop you might need to do only once if M is very, very large. But in general, taking anywhere from 1 through 10 passes through your data set, may be fairly common, but really it depends on the size of your training set. And if you contrast this to batch gradient descent, with batch gradient descent, after taking a pass through your entire training set, you would have taken just one single gradient descent step. So one of these little baby steps of gradient descent where you just take one small gradient descent step. And this is why stochastic gradient descent can be much faster. So that was the stochastic gradient descent algorithm, and if you implement it, hopefully that will allow you to scale up many of your learning algorithms to much bigger data sets and get much better performance that way.